Hi, welcome back to another extreme value theory video. Up until now, we've been considering the extreme values of single random variables or single stochastic processes. In this video, we're going to take that a little bit further and start to consider the extremes of multiple random variables or processes. So in general, the theory that we've developed has analogues in the multivariate setting. We're not going to consider the general multivariate setting in this lecture. We're only going to look at the case of bivariate extreme values, so we're considering the joint distribution of two random variables or two stochastic processes. This will demonstrate some of the key ideas from multivariate extremes while keeping the ideas fairly simple to introduce in this one short lecture. It's important that we consider the joint distribution of these random variables, particularly if we're interested in modeling not only a single asset, but a portfolio of assets. So for example, in this case, we might have a portfolio of two assets, one that is Siemens stock and the other is BMW stock. As we can see, there's some positive association going on between these in the plot. And if there's dependence between these at extreme levels, so note that these are negative returns, so we're interested in large values here. If these large values happen concurrently and we don't account for their dependence in our analysis, then what we're going to do is leave ourselves vulnerable to very large losses where we suffer a large loss from our BMW asset as well as a large loss from our Siemens asset. So how can we describe this extremal dependence? And can we just use an idea we've met already? For example, the correlation. So what I've got at the top of the slide here is just a reminder of how correlation is defined. And that's the correlation between two random variables, x and y. It's going to be the expectation of their product minus the product of their expectations, all divided by the standard deviation of each x and y. There are several drawbacks to using the correlation when we're interested in modeling the extreme values of a process. The first common to the modeling approach disadvantage that we saw right at the very start of the course is that this measure of dependence uses all of the data and focuses on the center of the distribution, when really what we're wanting to do is focus on the tails of the distributions. The second drawback is that in order for this correlation to be well defined, it's going to require the expectation of each random variable to be finite, the expectation of that random variable squared to be finite, so that the standard deviations are also finite, and finally the expectation of their product is also finite. So these are some quite strong requirements, and particularly when we're dealing with heavy-tailed distributions. The third drawback of looking at the correlation is that this measure is going to depend on what the marginal distributions of x and y are. If we choose to measure y on a different scale, then we're going to get a different correlation value out from here. And the final drawback that should always be borne in mind when using a correlation in any setting is that it only fully describes the dependence between x and y if they follow a bivariate normal distribution. Otherwise, we're missing vital information about this dependence by only summarizing it using the correlation. Okay, so one of our issues here was that the marginal distributions of x and y are impacting our dependence measure. So if we're constructing a way of measuring this dependence, what we're wanting to do is to assume a particular marginal form for x and y, and depending on the random variables we're actually modeling, we can then use the probability integral transform to map them onto those margins. So the first way to do this is to simply use the empirical CDF for all values of x and a separate empirical CDF for all values of y, and to pass our observed values through these to obtain our observed values on standard Frechet margins. This isn't going to be particularly useful when we start considering very large values of x and y, because our sample only goes up to a certain point. What we can do instead is to combine a main body empirical CDF up to some threshold in each of x and y, and then fit a GPD tail model to each of them in order to construct a combined body and tail model for each random variable. Using that combined CDF, we can apply the probability integral transform and obtain our observations on standard Frechet margins. Great, so if we're considering these two random variables, x and y, on standard Frechet margins, then we can obtain analogous results to our univariate extreme value distributions, but in this bivariate setting. These results aren't quite as strong as the ones in the univariate setting, so we obtain only that the joint distribution function of x and y is going to have the form of e to the minus v of x and y, where this v here is a function, and it's going to map from pairs of positive values to a single positive value. Additionally, it's going to satisfy the property that a times v of y is equal to v of x over a and y over a. And the formal term for describing this function v is that it's homogeneous of order 1. So this result we're not going to use any further. I just stated it so that you're aware of it. But if you're interested in looking into this a little bit further, into the details of this bivariate extreme value distribution, or how it can be used in terms of modeling extreme values, then I recommend you look at Chapter 8 of the recommended text by Coles. In this lecture, all we're going to focus on is describing and not modeling the bivariate extremal dependence. So what we're going to do is construct a measure eta that is going to describe our dependence between two random variables at extreme levels. And we're going to be considering those on our standard Frechet margins. So here we're assuming x and y are both Frechet, where we've obtained these from our original sequences, which I'll call x star and y star. A very general assumption on these transformed random variables is going to be that their joint CDF, their joint survivor function, evaluated along the diagonal, so evaluated at xx here, it can be described by a slowly varying function L multiplied by x to the minus 1 over eta. So looking at this in a bit more detail, this is the probability that both x and y are greater than little x, and that's going to be approximately given by some constant c multiplied by x to the minus 1 over eta as x becomes large. And here we can make this approximation that L of x is approximately constant because it varies very slowly as x changes. What this gives us is a parameter eta between 0 and 1 that describes the tail dependence between x and y, and we'll look into that a little bit more shortly. But essentially what eta gives us is a way to describe how likely both x and y are to be extreme at the same time. So let's have a little look into how we can interpret the parameter eta. In order to do this, we're going to consider the conditional probability derived from that joint survivor function that we had before. And this is going to be the probability that y is bigger than some large value denoted by lowercase x, given that x is also greater than that value lowercase x. And following on from that expression we had before, this is going to be given by c times x to the 1 minus 1 over eta. When our parameter eta is equal to 1, then we can see that 1 over eta is also equal to 1, and this x term disappears from our conditional probability. So the conditional probability of y being large, given that x is large, doesn't depend on what we're defining to be large in this case. When eta is less than 1, that probability is going to change as we increase this value lowercase x. And it's going to specifically be that the probability that y is also large is going to be non-increasing as our definition of large increases. So as our value little x becomes bigger, the probability that both x and y are large together is going to be strictly decreasing. And that decrease, the decay in the probability, is going to happen faster as x becomes large, the smaller the value eta takes. Okay, so we've already seen how we can define and interpret this parameter eta that gives us a coefficient of extremal dependence, but how can we go about estimating it? One way that we can go about doing this is to come back to our previous joint survivor function here. So this should say survivor, not just distribution. And what we have is the probability that both x and y are greater than this little x value is given by this approximate expression. What we can notice here is that this is very similar to something that we saw earlier this week. And what we can do is use the method of Hill estimation to obtain an estimator for our parameter eta. The way we do this is to define this set of random variables z to be the minimum of each xy pair. What we can then do is look at estimating eta over this collection of n observed values for z as the sample mean difference between the log of the zi values and the log of a threshold value u. So for a high threshold u, this is going to be a stable value. What we can also do is use the other part of our Hill estimation procedure to estimate the parameter at the front here, c, and that's simply going to be the sample proportion of exceedances of u multiplied by u to the reciprocal of our estimated coefficient of extremal dependence. Okay, so we already have a framework established to estimate both eta and c, and so we've got a way to describe our extremal dependence based on an observed set of pairs of x and y values. So how can we link this back to estimating the joint losses of two assets? The way we can do this is to define a joint return level, ZP, in terms of a value on this diagonal, in term, which is giving us values for our standard fresh A x value and our standard fresh A y value. We can then define the return value with probability p to be the point along the line y equals x, such that the probability that x is greater than that value and y is greater than that value is going to be equal to p. Using our Hill-based estimator from earlier, what we can see is that if we plug this into our approximate joint survivor function and do a bit of rearrangement, then we can estimate our joint return level ZP as Z hat P, where this is given by our probability P divided by the estimate of C that we obtained on the previous slide, raised to the power minus our estimated eta, again, which we obtained on the previous slide. So what this ZP is giving you is the value on standard fresh air margins that is exceeded by both x and y with probability p. While this is nice to be able to obtain, it doesn't really tell us anything back on our original margins. What we have to do is interpret this value by back transforming ZP using the probability integral transform to obtain values A and B on our original scales, X star and Y star, so that this return level is giving us a pair of an X value and a Y value that are jointly exceeded with probability P. Okay, so we've introduced quite a lot of new material in this lecture, so let's just have a quick summary of what we've learned. The coefficient of tail dependence eta is a measure of the extremal dependence between two random variables, and it takes values in the range between 0 and 1. Large values of eta mean that our two random variables are likely to be co-extreme, while small values of eta tell us that they're more likely to occur at extreme levels individually, where x is extreme by itself and y is extreme by itself. If we have an estimated value of eta that's around 1/2, what this is telling us is that the two random variables or two processes are approximately independent of one another at extreme levels. We've also seen that we can estimate this coefficient of tail dependence using a Hill estimation procedure, where we're considering the pairwise maxima of these two random variables. So these are the Z values that we constructed previously. And finally, a point that we haven't covered, but that I'd like to emphasize, is that in the same way that we construct an autocorrelation function for the correlation that we introduced earlier, we can do the same thing, but in an extremal setting using the coefficient of tail dependence. So for an ACF plot, we would typically construct the correlation between xt and its self-lagged at various increasing lags to see how dependence decreases at lags within a particular sequence. We can do exactly the same thing here by setting yt to be equal to the x process at lags of 0, 1, 2, and so on. And for each of those pairs of sequences, consider an estimated value for the coefficient of tail dependence and see how that drops off as our lag increases. That gives us a way of linking back this tail dependence parameter eta to our extremal index that we considered in previous weeks. Great, so that's everything I had to cover today and everything I have to cover in this course. I hope you found this video useful, and I'll see you in the lab sessions on Friday. Thank you.